Hi everybody, this is going to be a supplemental video to the instructions for your next virtual lab assignment, and that is Williamson ether synthesis. Specifically, in your virtual lab program, it is going to be called Williamson ether synthesis 1. All right, so make sure that is the worksheet that you use for the instructions, and that is the lab module that you open up. Okay? All right, I want to talk a little bit in general about Williamson ether synthesis, just to review a couple of things, and also give you a little bit more information about what I want from the for you guys to keep in mind while you're running the lab, and also while you're writing your lab report. All right? Let's talk about Williamson ether synthesis in general. And this is basically a particular type of reaction that applies, that sort of falls under the category of the reactions that we were doing in Chapter 7, right? Specifically, this is going to be an SN2 reaction that produces an ether. All right, and I don't know if we've talked about ethers yet. Ethers have this general form, ROR. It means basically you have an oxygen that's got a carbon chain on either side of it directly attached to the oxygen by a double bond. If you're looking at the specific atoms, this means you're always going to have a carbon to oxygen to carbon single bond linkage. Okay? And you can make these through just the very familiar types of SN2 reactions from alkyl halides that we've been learning about in Chapter 7. You can actually make ethers via SN1 or SN2 reactions. The Williamson syntheses specifically are going to use SN2 mechanisms. All right? So there's a couple of different ways you can go about this. So let's say this was our target. Let's say we were trying to make this particular ether. This is called diethyl ether. All right. One way that you can do this is to start off with an alkyl halide, right? And basically what you want to do when you look at the ether, kind of break it down into two parts. I'm going to take one of the alkyl groups and sort of put it with the oxygen, and sort of make that a group, and then take the other one and put it aside. All right. One way to do this is to take an alkyl halide and react it with a salt, either a sodium salt or a potassium salt that contains this OR group as a counter ion. So basically, this is called an alkoxide salt. And I'll give you an example of one in a second when I show you the specific reaction. All right? So you use an alkoxide salt, and you have to have a solvent. Remember, SN2 reactions work best with aprotic solvents. There are several of them listed in your book as examples. All right? And what's going to happen is the OR part of the alkoxide salt will replace this guy over here, and you'll end up with your ether. Whoops. And then you'll end up with X minus and whatever counter ion you had from the alkoxide salt, usually a sodium or a potassium. I'll just put a sodium here for an example. Okay? Now, if we're looking at how to make this specific ether, diethyl ether, right? Well, let's look here. Let's look at the structure, the part of the structure I put in a circle or oval. That's going to be the part that once contained your alkyl halide, right? So I could put something like this, right? 2-carbon unit corresponds to the 2-carbon unit in a circle, all right? We want to react it with an alkoxide salt. So, basically in the salt, I need this to be either a sodium salt or a potassium salt. Either one works, all right? In the example I just gave you a sodium, so I'll use a sodium. And then you want the ion, the counter ion, right, the anion, to be the OR minus. And that is, in this case, OCH2CH3. Right? When it's just sitting in the jar, it's, sodium ethoxide is the name of it. But when you put it in a solvent and it dissolves, it associates, it gives you Na plus, which we don't care about, and then OCH2CH3 minus. That's what acts as your nucleophile to come in, attack that carbon, bump off your Cl minus, and boom, give you your product. Okay, so that's one way that we can go about this, by using an alkoxide salt. There is another way that you can go about it. Basically, it follows the same principle, except for the fact that you're kind of creating the alkoxide ion yourself, instead of having it sort of self-generate from dissolving a salt. All right. So another thing that you can do is you can take an alcohol of some sort, right? And what you can do is you can do a two-step reaction. The first step is to add a very, very strong base. And when I say strong base, I mean stronger than your typical hydroxide ion, right? A very specific type of base is used for this, and that is the hydride ion. Hydride, I'll just draw it over here, is an H minus. Okay? And again, hydride just doesn't sit on the shelf. You have to get it as part of an existing salt. So you'd use something like sodium hydride to serve as a hydride source. All right? This hydride, I'll just draw it over here. This H minus is actually going to act as a base, and it's going to grab this proton, this H plus, and it's going to leave the pair of electrons behind on oxygen. So basically, that makes you produce an alkoxide ion in a different way, as opposed to the last one. But we still end up with the same species. Okay? You end up with H2 as a byproduct. You always know this is working because you produce H2, it's a gas, you'll see it bubbling up. Whatever you do, don't put an open flame to it. That would be very bad. All right? So that's the first step of the reaction. And then the second step is to add an alkyl halide, and you're going to get the same type of substitution reaction that you got last time, right? Where this comes in, attacks, and displaces your X minus, and you end up, whoops, keep forgetting I'm in general form here. You end up getting your ether. Okay, now let me show you, how this would work, in real life with a real example. Again, I'll use diethyl ether, right? So we need an alcohol. All right, in this case, the part in the rectangle with the O, that's going to represent what comes from your alcohol. So in this case, we have a 2-carbon unit with an O. Make sure that's an OH to start off with. All right, so we can add that. We can add some sodium hydride. And then the other unit here, the one in the circle, 2-carbon unit, that's going to be what composes our alkyl halide. So we could, again, put any type of alkyl halide that we wanted. We'll just use a chloride. Oh, one thing I forgot. I forgot to put in the solvent again. I still need an aprotic solvent. So don't forget that. And when all is said and done, that gives you your ether. Okay? All right, so those are the two general ways to do a Williamson synthesis. Now, even within certain examples, you can have a couple, within a certain way of doing it, you can still have a couple of subdivisions. For example, let's say instead of trying to make diethyl ether, we were trying to make something like this, right? Ethyl methyl ether. In this case, the two R groups are different. So what's kind of funny is, like, let's say you were doing this the first way, right, by using an alkoxide salt. There's a couple of different options you would have. You could make the alkoxide salt based off of this, right? So that would be like something like sodium or potassium ethoxide. And then this group over here would be the one carbon unit that was made your alkyl halide, right? Something like CH3Cl or something like that. Or you could do it another way. You could lump this together. You could use sodium methoxide as your alkoxide and then use a 2-carbon, rectangle, sorry, 2-carbon alkyl halide as your other species, right? So there's different ways of doing this. In your lab, it's going to ask you to do a little bit of thinking on your own, right? It's going to give you a target compound to synthesize. I think, off the top of my head, it is benzyl methyl ether, which is going to look like this. Double check that, please, to make sure I'm not wrong, but I'm thinking that's what you're going to try. So it is going to be up to you to use the species, the ingredients that you have at your disposal to figure out a way to make this. Okay? So it won't tell you exactly what to use, but it will tell you in the instructions the general steps. All right? Okay. Here are some general notes and additions I have to give to the provided lab instructions. All right, so this is basically what to expect. It can be a little confusing at first, all right, because it tells you, I think in the instructions, it's going to tell you to take some materials, it'll tell you to take reactants that you need and add them to the round bottom flask while it's still sitting up on the shelf. Then it's going to tell you to add a solvent. Then it's going to tell you to move to the clamp, and then it'll tell you to add some more reagents. All right, so this can be a little bit confusing. I'm going to give you a little bit of hint here. All right, initially, when it tells you to add any reagents that you need while the round bottom flask is sitting on the shelf, you're only going to need one. All right, add one reactant. And your solvent, and it tells you what to use as a solvent, to your round bottom flask while on the shelf. All right. So then it's going to tell you to drag the round bottom flask to the clamp. All right. After it's in the clamp, that is where you add any other reagents that you need. All right. So a good thing to do before you actually get into this is to kind of doodle on some paper. Maybe use these methods to figure out a couple of different possibilities for how to synthesize this target compound. And then it'll be easier for you to look and see if they have those components or not. All right. So from there on, it's pretty simple. It gives you very stepwise instructions like it did last time for how to do things. You're going to be doing a couple of analytical techniques in this. You're going to be doing TLC, and you're going to be doing IR. All right, so let me tell you about TLC. All right, much like we did last time, we're going to use TLC to monitor the reaction progress and tell us, sort of help us to indicate disappearance of reactant, appearance of product. All right? So, you're going to take 4 TLC measurements. TLC 1 is going to be after you've gotten everything mixed up, but before you actually start the reaction. So you don't start the reaction until you hit the little knob on the stir plate. So take a TLC beforehand, all right? You're probably going to see one spot. That should correspond to one of your reactants. All right. Only organic species show up. I take that back. Let me backtrack that. I'm just going to say only one of your reactants is going to show up on this. So you're probably going to see one spot. I just want to highlight one thing. You're never going to see the solvent show up on this. So, whatever solvent that you use for this reaction, whatever aprotic solvent, it's not going to show up. All right. It's just going to be reactants and products. All right. Then I want you to take a TLC after 1 minute of reaction. All right, you should see more spots here. All right, I'm not going to tell you how many. I will tell you something about the bottom one, though. There's going to be one that appears at the very bottom, very, very close to your origin. That bottom spot is a waste product. So that bottom spot you don't really need to worry about. It's any other spots that are important. Okay? Then you're going to do TLC 3 after 15 minutes. And hopefully by now the spots of interest are changing and you can tell something about it. All right, at this point you can stop the reaction and you can follow the instructions to set up an extraction and get the organic layer. And finally, your last TLC is going to be after you do the extraction. After the extraction, you remember this waste product here that I mentioned that showed up? That should go away by the time you get to TLC 4. Okay? So, I want you to do these. I want you to measure the RF values for any of the spots that appear in the right-hand lane on these. And also, much like last time, comment on their changing appearance and what that means. Right? What is disappearing, what is appearing. All right? And then the last thing you're going to do here is you're going to do an IR spectrum, and this is very simple. It tells you in the instructions how to do this. You basically just drag something from the IR spectrometer to the liquid, and it magically gives you an IR spectrum of what's in there. All right? So, in your IR spectrum, what you need to do is, much like you did in your problem sets that I gave you a couple of weeks ago, indicate important, I want to use IMP for important, signals. Give me some specific wave numbers. Tell me that you have a strong, sharp peak at 3,000 or whatever wave number it is. All right? And tell me, in turn, what that indicates about functional groups that you think are present. Okay? Share your results, or sort of compare your results in the IR spectrum to your target compound. You know the structure of your target compound. Does that match up with the target compound? Were you able to successfully synthesize it according to the spectrum? Were you not? Tell me what you see. Okay? All right. Lastly, in your lab report, this is basic. What I'm telling you right now is basically the results. You know, I've told you what I want as far as the TLC. I've told you what I want for the IR. You're going to want to explain those results in your analysis conclusion section. For the introduction, I want you to give me a little bit of background on Williamson ether syntheses in general, how they can be conducted. I want you to lead into a discussion about your particular lab, what you particularly are trying to synthesize, and your strategy for going about it, right? What pathway did you pick? What reagents are you using, etc. Okay? Okay, so you guys are free to do this on your own time. If you will get the lab reports back to me in a week or so basically a week from your normal lab period will be fine. Okay, and if you have any questions along the way, just let me know. All right, thanks, and I will see you later. Bye-bye.